left you in section 8.1, where we were talking about sequences. Remember that a sequence is a list of numbers divided by commas. Okay, so a list of numbers in a very specific order. And even though I don't write this up here, what we're talking about are infinite sequences. So they're a list of numbers that goes on forever and ever and ever. And I left you with an example where the sequence was 3, negative 3, positive 3, negative 3, positive 3, negative 3, and that pattern continued forever and ever and ever. And the goal here was, I gave you the sequence, and this is one way to write a sequence, is to write it within the curly braces and have the numbers. You cannot switch the order of these numbers in any way, shape, or form. They must stay in this order. The 3 dots at the end tell me that this sequence goes on forever. And what I asked you to figure out was a formula for AN. Now, it's important to know what we're starting with up here. And in our textbook always starts with the first number, so A1. Some textbooks will make this very first number A0, and so you just need to know what the context is that you're looking at. But in our case, we're almost always going to be starting with A1, and then we have A2, and A3, and A4, etc. And our goal for today was, I asked you to go home and think about, can you come up with a formula for the nth term in the sequence? All right, so if you've thought about this, and even if you haven't thought about this, I'd like you to say hello to your neighbor.
Yo.
And I'd like you to share your ideas with your neighbor about what your formula will be for AM.
White gap.
Well, it's 1.
I have a neighbor who had a good idea for this.
Looked like he had a good idea.
All right, so anybody want to share your neighbor's ideas?
Sure.
Okay.
3 times a negative 1 to the n minus plus 1.
Okay. All right, so 3 times negative 1 to the n plus 1. All right, will you explain why this might make sense?
Well, every time you have a positive exponent, it's going to be a positive 1. So that's going to give you the 3 to begin with. Then as you go to n being the second in the sequence, you'll have a negative exponent, which will cause that negative 1 to be a negative 1 times 3, which is a negative 3
Okay.
on down the line.
All right, so this seems like a pretty good idea. And this idea of taking negative 1 and raising it to a power, and having that power go from odd to even, or vice versa, even to odd, even to odd. This idea, you're going to see this a ton on these sequences and eventually these series as well. And so if you want to be able to alternate a sign, going plus to minus, or minus, plus, then an idea of taking negative 1 raised to a power is going to help you to do that. Did anybody come up with a different formula for AN?
3 cosine of n, 3 times cosine
I know.
n pi.
3 times cosine of n pi. Okay, will you explain why this one makes sense?
Just because the line just keeps going up and down, and the 3 would be the amplitude, so it's just, so at every pi it becomes y is either 3 or negative 3.
Okay, so when n is equal to 1, we end up with cosine of pi.
Which is,
What's cosine of pi?
oh, that's
That's 0.
No.
Oh,
Negative
no.
1.
Negative 1, negative 1, negative 1.
Negative 1. Okay, so then we have negative 1 times 3. So we might need to adjust this a little bit.
Yeah,
So how could we adjust this?
So put a negative sign in front.
Okay, so yeah, we can take this, and if we put a negative in front of the 3, then this one's going to work to have us start with a positive 3 at the beginning. So this would work as well. And this is another really good way to come up with an alternating plus and minus sign. So if we have cosine of n times pi, we know that cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1. And so as you increase n by increments of 1, then this cosine value is going to go from plus and minus 1, it's going to bounce back and forth. So here's a second way to come up with an alternating sign. Okay, other ideas, anything different?
I'm still a little bit confused on the first example as to how your exponent becomes negative, because if you're just adding, I'm just confused.
So I think Jeff might have said that the exponent went negative, but I think what he meant to say was the exponent was odd or even. And so whether your exponent is odd or even makes this entire -1 to the power either positive or negative.
Gotcha, okay. Makes sense.
Could you also make it n minus 1? And have the same result?
Okay, and is 3 times -1 raised to the n minus 1. And yeah, that's going to work too, because the difference on the powers is that you want to have your power be either even or odd. And so if we subtract 1 from the power on the first one, we'd have -1 to the 0, which is also 1, positive 1, giving us 3. So this would work as well.
As long as the n is greater than 0.
Well, in the case of raising -1 to a power, it doesn't matter whether your power up here is positive or negative. So there, it's going to be okay. Yeah. All right. Anybody come up with any other ideas?
-3 times -1 to the n.
All right. So this is also a good formula because here this is sort of similar to Cisco's idea where the alternating plus and minuses doesn't quite work out up here. So for example, -1 to the 1 is a negative value, but we really want positive, so let's fix that by putting a negative in the front. So that works as well. Cool. All right. Other ideas?
You can also use sine, you can use cosine, so pi over 2, -3 sine pi over 2.
So -3 times the sine of
Probably n pi over 2.
Yeah, pi over 2.
n pi over 2.
Does that work?
And then just erase the negative above 3.
Oh yeah, and that negative wouldn't be there.
Yeah, and we have a small problem because with this n up here, when n is equal to 1, we have a pi over 2. When n equals 2, we end up with pi. And so this guy is going to actually give us, we're going to have trouble with this guy because it's going to give us all 4 quarters of the circle. Alright, so, but I think we could probably mess around with this, and I want to encourage you to think about how you might mess around with that a little bit more to just get the top and the bottom of the circle. There it is. Okay, so the moral of this story is that there are many, many different possible formulas that we can use to describe the exact same sequence. Okay? So the two things I want you to get out of this thought exercise here is, number one, that we can have many different formulas to describe the exact same sequence, number one. And number two, that when you have an alternating sign, a really good way to think about how to administer that alternating sign is to take -1 raised to a power where that power increments, goes even, odd, or using something like a cosine function where you can bounce between positive, negative. And so these are really good ways to make an alternating sign in your sequence. Okay, all right, are there any questions first of all, on this example? Are there any questions in section 8.1 on the practice problems? I assigned numbers 1 through 8.
I need to start.
Just in general, like 8 was kind of tricky, I thought. But in coming up with the formula for those, is there some sort of method? Just
Yeah,
I mean,
that's what I was gonna ask. You just gotta conceptualize it, or?
Yeah, so these are problems where you're definitely getting your hands dirty.
right.
So, for example, I think 8's a good one to talk about because it is an even number, and I do agree with you that this one is definitely a tricky one. So this is section 8.1, number 8. And our sequence is 5, 1, 5, 1, 5, 1, etc. All right, so Jeff, you mentioned this one was tricky, but then you ended up coming up with a.
Well, I didn't really come up with it, I talked to somebody about it, so.
Okay, well, what were your initial thoughts when you looked at this?
Well, obviously, every they're all odd, but you've got, start out with 5, but you gotta subtract 4 from the next one and end up with 5 again, so. You've gotta have some power of, I guess, an odd power of an even number, maybe to get 4. So-
Yeah, so this one we've got, it's kind of alternating in the sense of it's bouncing back and forth between two numbers, but it's not a plus and a minus that are going on here.
Right.
So one thing that I might do is I might try to draw a picture of this sequence and draw a graph. And so when I draw that graph, let's see, I need 1, 2, 3, 4, 5. So A1 is 5, A2 is 1, A3 is 5, A4 is 1, A5 is 5, etc. And so these numbers are bouncing back and forth. And one thing that I might notice when I start to look at this picture is that these guys are bouncing back and forth across some kind of an imaginary line in here. What is that imaginary line that's splitting these numbers up? Yeah, if I draw a dashed line here at about 3, then what I see is that these numbers that I'm looking at are bouncing 2 above 3 and then 2 below 3. And so it's almost like I'm looking at 2, -2, +2, -2, and then lifting it up by 3. And so one way that I could think about this sequence is I could say AN is equal to 3 plus, and then I'm going to be adding 2 and then subtracting 2. So it's almost like this sequence over here where I'm looking at +2, -2, +2, -2. So I could use any of these possible versions here. So for example, if I go with the first one, I've got 3 plus 2 times -1 to the n plus 1. And so it's almost like over here, I bounced up and down above and below y equals 0. On this one, I'm bouncing up above and down below y equals 3. So I'm adding 2 on, and then subtracting 2 off, and then adding 2 on and subtracting them off. And so I can see that as soon as I start to see two numbers alternating back and forth between each other, I might ask myself, okay, what's the center line? What's exactly halfway between those two numbers? How can I bump up or drop down to those two values?
But then in the same sense, couldn't that also be a cosine curve that shifted up?
So that's absolutely right. I could take this one, and so an alternate way to think about this is I could say AN is 3 plus, well, actually, so then if I wanted to use this one here, then it would be 3 minus 2 cosine of n pi. So I could do that as well. Absolutely. And I could do the same. I could use 3 minus 2 times -1 to the n. I could use any of these versions where instead of bouncing up and down by 3, I'm bouncing up and down by 2, but it's been shifted up. All right. Questions or comments about that? Okay. Questions or comments about any of the other 8.1 practice problems? So you should expect on these problems right here, especially the very first night that you look at them, you should expect to feel frustrated. And you should expect to feel that I have no idea what to do with these. And as we continue to work with these problems, you're going to get, right now your toolbox of sequences and series tools is very empty. And as we continue to work with these, that toolbox is going to get filled up, and you're going to have a lot more ideas, and you're going to look back at one of these later on, maybe toward the end of this, in a few weeks, and say, oh, that one's really easy for me to look at now, I can see it, and look, it bounces up and down. So right now you should expect to be a little bit frustrated and expect to think that this stuff is hard, and later on you're going to come back and see it, and you're going to say, I'm so experienced in this, I'm a rock star. Okay. Dennis?
And you think that would be a good way to start on all of them, is just write like a graph and just write your points and just do that?
I think it's a really reasonable way to do it. It's one option, one way to get your hands dirty with it.
Well, because that way I kind of see it.
Yeah, and so I think it's a really good, at least one option to look at when you're messing with these. Good. All right. So what we started with last time, I gave you a couple of examples of sequences, and so from our last class, we looked at 3 examples, and the first one was an is equal to 1 over n. And so if I'm given a sequence, and it's just written as a formula, an equals 1 over n, that's a fine formula, but I may want to write out some terms. And so my first term is going to be a 1. My second term will be 1/2, because n will be equal to 2, and then n equals 3 gives me 1/3, 1/4, 1/5, etc. And so I can write my sequence with my curly braces and then separate the numbers in my sequence with commas and have 3 dots at the end to say it goes on forever. And I can also draw a picture, a graph of the sequence. And so I might write out a few of my terms, maybe the first 5. And so I can draw the dots. When n equals 1, my height is 1. When n equals a half, or I'm sorry, when n equals 2, my height is a half. And then a third, and then a quarter, and then a fifth. So that was our first example of a sequence. Our second example was an is equal to 2 plus -1 to the n over n. And so in class last time I asked you to write out a few of the terms, and many people went ahead and typed them into their calculator and found some decimal approximations, but I think it's nice to actually leave the formula up and not actually simplify things too much. So I would have 2 minus 1, and then I've got 2 plus 1/2, and see I'm getting that, there's my alternating term on that top there. It's going to go from negative to positive to negative, 2 minus 1/3, and 2 plus 1/4, and my sequence goes on for a while there. And what's nice about this is that I can see that my center number there is 2, and then I'm subtracting or adding numbers onto that too. And so my picture looks something like this. So I'm going to give myself a dashed line here at y equals 2 to help guide me. And when n is equal to 1, a1 is equal to 1. When n equals 2, I'm going to add a half onto 2. When n equals 3, I'm going to subtract off a third. When n equals 4, I'm going to add on a quarter. When n equals 5, I'm going to subtract off a fifth. And our last example, the one that we were wrapping up today, was the example where an is equal to, and we had lots of choices, but I'm going to go with 3 times -1 to the n plus 1. And so the sequence looked like positive 3, negative 3, positive 3, negative 3, etc. And our picture bounces back and forth. We have a height of 3 when n equals 1, height of -3 when n equals 2, and positive 3, negative 3, and positive 3. Okay, now these were the 3 examples that we had, and I'd like you to take a look at these 3 pictures. The very first picture over there, when an was equal to 1 over n, I can almost in my imagination, and I'm not going to do this on the board, but in my imagination I can almost fill in the gaps on here, and this looks like y equals 1 over x. And as we go farther out along the horizontal axis, as n gets really big, the height of these dots is getting closer and closer to a height of 0. And so, kind of going along, these dots are getting closer and closer to y equals 0. In our second example, where an is equal to 2 plus negative 1 to the n over n, these dots are bouncing back and forth. They're alternating above and below the line y equals 2. But as that's happening, even though they're bouncing back and forth above and below, they're kind of getting sucked in. And so they're getting closer and closer to that line y equals 2. So as n gets really big, these dots are approaching y equals 2. Now in this last example, this one's a little bit different. Because in our third example here, our dots are bouncing back and forth above and below y equals 0, but they're not getting any closer to y equals 0. They're staying 3 above, 3 below, 3 above, 3 below, 3 above, 3 below, 3 above, 3 below, and they never actually get any closer to y equals 0. And so somehow there's something different going on with this last sequence right here. And so the question that we're looking at here is, what is the trend of these sequences? What happens with these sequences as n gets really big? And so now I'm talking about allowing n to get really big. What does that sound like? It sounds an awful lot like a limit. Alright, so here's our definition. A sequence, an, has a limit, L, written the limit as n goes to infinity of an equals L, or we can write this as an approaches L as n approaches infinity, if we can make the terms of the sequence as arbitrarily close to L as we like by taking n to be sufficiently large. If the limit as n approaches infinity of an exists, then we say the sequence an converges. Otherwise, we say the sequence diverges. All right, so in Calc 1, we started out, very beginning of Calc 1, talking about limits. And limits turned into being able to talk about derivatives and integrals. And so talking about limits really opens up a bunch of doors. And here we are back with limits again, with this whole new idea of sequences. All right, so a sequence an has a limit L, written the limit as n approaches infinity of an is equal to L. That looks an awful lot like, there's our function name, and here is the y value that we are approaching. And we're allowing the x value, the horizontal value, to get really big. In other words, we're walking really far down the x-axis, really far down the horizontal axis, and looking at what happens to the height of our function. And if you want to become a little bit a little bit more friendly with your limit notation, you can say an approaches L as n approaches infinity, and that's legitimate notation as well. And so we have this limit if we can make the terms of the sequence as arbitrarily close to L as we like by taking n to be sufficiently large. Now, when you go and you take advanced calculus, then you're going to learn about things like epsilons and deltas. And so your epsilon is how close you get to the value of L, and your delta, well actually delta doesn't apply here, but your epsilon talks about how close you're going to get to this L value. And so what's happening is as we walk down the horizontal axis, we allow n to get really, really large. Can we get as close, can we keep our dots within a sufficiently small range around the limiting value that we think we have? So for example, I'm going to leave this picture up here. For example, with an equal to 1 over n, the limit, and I put a little tube, a tiny, tiny tube around y equals 0. There's my little tube around y equals 0. If I walk far enough out on this horizontal axis, once I walk far enough out, then all of these dots are going to stay within this tube that I'm looking at. So I can make this tube sufficiently skinny, I can make it as arbitrarily skinny as I want to, and however skinny I make it, eventually I can walk far enough out on this x-axis that all of my dots will be within that tube. And that's what we're talking about with the limit. Alright. For this guy over here, for an equal to 2 plus negative 1 to the n over n, the limit as n approaches infinity of 2 plus negative 1 to the n over n. Well, if I look at this, it looks like, just sort of based on the picture here, these dots are getting closer and closer to this line of y equals 2. And so if I draw a really skinny tube around y equals 2, so make the terms of the sequence as arbitrarily close to L, arbitrarily as close to 2 as we want to make a little skinny tube, by taking n to be sufficiently large, meaning once I make this tube, if I walk far enough out on that line there, if I keep walking to the right, eventually all of my dots are all going to fall within this tube. They're all going to get sucked into the muck. And so we say that this limit is equal to 2, because our little tube is surrounding y equals 2. Okay?
Would it still converge if the limit was infinity or negative infinity?
That's a good question. The answer is no. No, the tube that you make must be surrounding a finite y value. All right, so I'm kind of turning the tables a little bit here on our definition of limit. I'm making it a little bit slightly more precise than, and with more technical verbiage than you had in your Calc 1 class maybe. Are there any questions about what we're talking about here? Okay, well let's look at this third sequence here. This third sequence that we have is an equals 3 times negative 1 to the n plus 1. And so I'd like to know about the limit as n approaches infinity of 3 times negative 1 raised to the n plus 1. And so now I ask myself, are these dots getting closer to any one specific y value? And, all right, yeah, and it looks like maybe you might say no. But some of you might be saying, well, yes. They're bouncing back and forth across this y equals 0 line. So I might think, oh, well, let me try and, I'm going to put a question mark here and say, well, this limit is equal to 0 because they're bouncing back and forth above and below y equals 0. But I'm going to put a little tube here. around y equals 0. And no matter how far out I walk along y equals 0 over here, my dots are never going to end up in the muck. They're never going to end up in that tube, no matter how far out I go. Or I might try, oh, well, maybe the limit's equal to 3. So then I put a tube around the 3 up here. And so now I walk along here, and look at all these dots that are showing up here in the tube. Is my limit equal to 3? No, why not?
Because you got the ones on the bottom.
Yeah, they're not all there. Still got these pesky guys down below here. And so even though what we have to make sure happens is that when we make a really skinny tube, every single dot beyond a certain point falls within that tube. Okay? And so here we're very sad because we're missing some of the dots down below. Our tube that we tried in the middle here also did not capture all of the dots. And so in this case up here, this limit does not exist. And so this sequence, an equal to 3 times negative 1 to the n plus 1, this sequence diverges. The other two sequences converged. So even though our idea of diverging is things explode up to infinity or explode down to negative infinity, and that's our idea of diverge, well, a sequence can be a divergent sequence even if the numbers are just bouncing up and down between two finite numbers. So diverge means that the sequence does not settle into one specific y value. Okay.
So it's proper to say divergent and there no limit exists. It's the same thing then?
That's right.
Okay.
That's right. And most of the time, the vocabulary that we'll end up using is determine whether the sequence converges or diverges.
Mhm.
And if the sequence converges, determine its limit. Okay, so we've looked at some pictures here, and some of the pictures we can look at these and say, yes, this sequence converges. And in fact, we know an awful lot about 1 over n because we know a lot about the function f of x equals 1 over x. And as x got really big, the y value of the function gets close to 0. The same thing happens here. As our denominator gets huge, 1 divided by a huge number is very tiny. And so we know about that type of tool. And we know about looking at these numbers that are bouncing back and forth. And on this example, our dots bounce back and forth above and below the line y equals 2. But I kind of just identified this as, look, I can draw a tube, and look, it looks like they kind of end up staying within that tube eventually. And so this was kind of shady. This is a little bit of math magic. And so the real question that we have next is, if we have a sequence fancier than an equals 1 over n, how do we determine whether the sequence converges or diverges? And so we're going to take a 10-minute break, and when we come back, we're going to learn about tools to test if a sequence converges or diverges. All right, so please take a 10-minute break, and when you come back, we're going to collect together some tools for that currently somewhat empty toolbox. In Calc 2, these ideas are kind of floating back up to the surface. The idea of limits, the idea of what happens as these dots get close to a certain y value. And so the idea here is that we want to build our toolbox test to see if a sequence converges or diverges. So we are not interested in limits as x approaches some specific number. We are focused completely on looking at as x, or in our case with sequences, n approaches infinity. So we're talking about what happens to these dots way, way, way down the line. And so here are some tools that we have. And in fact, I'd like you to take about 10 seconds now and sort of recall back through Calc 1 and the beginning of Calc 2, where you've talked about limits before, and some of the different ideas that have popped up. So kind of think about that for a second. Back to that stuff. All right, now I'm going to remind you of some of those things. So we have some basic tools to look at whether a sequence converges or diverges. And so the very basic tools are that we can use this limit symbol in the same way that we did way back in Calc 1. And so limits of sums, differences, meaning adding and subtracting, products, etc., portions, are the same as sums, differences, products, etc., of limits. Alright, so that sounds really confusing. I mean, it sounds like I just said the exact same thing. Limits of sums, difference, and products are the same as sums, difference, products of limits. So what that means, my thought bubble here, is that if I have the limit as n approaches infinity of one sequence plus a second sequence, an plus bn, that's exactly the same. So this is the limit of a sum is exactly the same as the sum of the limits. So in other words, you can distribute that limit sign through addition and subtraction. And just like in limits, but very, 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 very unlike derivatives, if I have the limit as n approaches infinity of an times bn, there's no such thing as a product rule with limits. With limits, we can take the limit of each term individually. So the limit as n goes to infinity of an times the limit as n approaches infinity of bn. And so we can move these limit symbols, whether we distribute them across multiplication or across addition, totally valid as long as all of the limits that we're talking about all exist. And so you should see the whole list of properties, which is in your textbook. So you should read about the limit laws for sequences on page 414. I'm not going to write all of those out on the board, but you can check them out there. Okay, so that means that all of the sort of limit techniques and rules that we have used before, we can still use with sequences. And so let's look at an example here. If we have the sequence an is equal to n to the fourth plus n plus 1 divided by 6n to the fourth minus 5. Okay. So suddenly this sequence is much more complicated than the first couple of examples that we looked at. And the question is, does this sequence converge or diverge? And so by asking this question, what we're asking is, if we graphed this sequence and we plugged in n equals 1, n equals 2, n equals 3, and we plotted those dots, do the dots sort of converge to or get close to some particular y value? And if the answer is yes, then the sequence converges. If the answer is no, then the sequence, we say, diverges. And so to answer this question, we want to answer the question, what is the limit as n approaches infinity of n to the fourth plus n plus 1 divided by 6n to the fourth minus 5. Now there's a ton of different techniques for calculating this limit, and the really short answer here is I've got a rational function here, I've got a polynomial divided by a polynomial, and if you have a rational function like this, what is the quick and easy and dirty way to figure out whether this function approaches infinity, approaches 0, or approaches some number? What do we want to look at?
Because of the shared degree, can't those two degrees be considered zeros, and then you can take n plus 1 over negative 5 and just assume that's a really large number divided by a piddly number, so its limit is infinity.
Okay, so your idea about looking at the highest power is a big idea, okay? So when I look at these highest powers, as n gets really big, for really large values of n, this minus 5 is doing nothing. I mean, we have 6 times a bajillion raised to the fourth, and then we're going to subtract off 5. I mean, really, who cares about that 5? So this 5 becomes insignificant for really large values of n. The same with the plus 1. I mean, if you have a bajillion dollars raised to the fourth plus an additional bajillion dollars, and then you add one more dollar on, you're not going to care about that one extra dollar right there. So we don't care about the 5 and the 1. And in the long run, if you have a bajillion dollars raised times a bajillion dollars times a bajillion dollars times a bajillion dollars, and you add on an additional bajillion dollars, you really don't even care about that. And so what happens is, as n gets really big, all the terms that are not n raised to the highest power, all those terms become insignificant. And so we can look at just the n raised to the fourth on the top and the bottom. And since those are the same powers, the coefficients in front of those are what we're going to be looking at. And so this limit is equal to 1/6. So that's the quick and easy way to look at this limit. If I want to be a little bit more precise about this, then I can also look at this limit and say, okay, I've got the limit as n approaches infinity of n to the fourth plus n plus 1 divided by 6n to the fourth minus 5. And I can look at my highest power in the denominator. Look at the highest power in the denominator. And then multiply. So in this case, our highest power in the denominator was n to the fourth. And then we can multiply the numerator and the denominator by 1 over n raised to that highest power. So the slightly longer algebraic way to come up with 1/6 is I can take the limit as n goes to infinity of n to the fourth plus n plus 1, multiply that by 1 over n to the fourth. Do the same in the denominator, 6n to the fourth minus 5 times 1 over n to the fourth. Totally legitimate, because I'm multiplying the top and the bottom by the exact same value, so I'm not changing the value of my expression. And now I can distribute. And I've got the limit as n goes to infinity. In my first term, I have n to the fourth over n to the fourth, so that's 1. Plus 1 over n to the third when I do my simplifying. Plus 1 over n to the fourth. And in my denominator, I end up with 6 minus 5 over n to the fourth. All right, are there any questions on how I came up with this expression down here on the bottom?
Could you go over that one more time?
Yes. So I'm gonna let's take this top part here. What I'm really doing is I'm distributing the 1 over n to the fourth to the first term, so that becomes n to the fourth over n to the fourth. My second term will be n over n to the fourth, and then my last term will be 1 over n to the fourth. And so once I simplify, then I end up with these guys here, because I can cancel those n's. Good. And same on the bottom. Okay, other questions about coming up with this expression here?
Now it's the opposite, right, where everything that has an n in it is getting so unbelievably small that it doesn't matter.
That's
Zero.
exactly right. And so what we have here now is, as n gets really big, 1 over a huge number gets unbelievably small, and so 1 over n to the 4th is going to go to 0. 1 over n to the 3rd will go to 0. And 5 over n to the 4th is going to go to 0. And as n gets really big, this 1 that's sitting by itself is not affected at all. And the 6, which is sitting by itself, is also not affected at all. And so, in the end, as we calculate this limit, we now have 1 plus 0 plus 0 and 6 minus 0, and we end up with 1/6. So technically, when we look at the highest powers on the top and the bottom over here and they match, really what we're doing is shortcutting this algebra right here. Okay, and you are welcome to use either method. You might want to remind yourself what happens when your powers are different. If your power is bigger on the top, then things are going to explode and your limit will go to infinity. If your power is bigger on the bottom, your entire function will go to 0. But the same idea happens. Okay, any questions or comments about that? Okay, great. So that is our first sequence. Now, the final conclusion on this is that this particular sequence converges to 1/6. So after I've done the mathematics that goes into that, either the shortcut or the longer algebra version, then our sequence AN converges to 1/6. That's our final conclusion. So if we graph our sequence and do enough dots, eventually, it might look really crazy at the beginning, but eventually as we walk down here, eventually those dots are going to be converging to and sort of floating in on y equals 1/6. Okay, so that's our first example. All right, second example. Our sequence AN is equal to the natural log of n over n. And we would like to determine whether this sequence converges or diverges. Okay, so our first technique, the first technique that we're going to put into the toolbox is, if we have a rational sequence, we can look at highest powers, or we can do the algebra. In this particular one, because of this natural log, I can't do that highest powers trick. It's not going to work for me. Now, when I look at this, and the goal here is to calculate the limit as n approaches infinity of natural log of n over n, when I look at that, it kind of reminds me of something that we learned earlier on in the semester. If I rewrote this, so if I see this and I go, oh, look at this. Earlier in the semester, we might have looked at something that looked like the limit as x goes to infinity of the natural log of x over x. What technique might we have used to figure out this limit? Do you remember anything from way early in the semester? Technique?
Oh, when we talked about convergent or divergent, you gave us an example of 1 over x versus 1 over x squared, and explained how the higher degree in the denominator would clamp it down to 0 faster. Does that have any relation?
Okay, so you're thinking about areas versus height of curves.
I just
Going back to what you
Since
said,
that's just a single,
so what you were saying earlier, couldn't you take the, just break it into pieces and divide it into limits?
Okay, so the thing I was saying earlier about we could split it into a top limit and a bottom limit, that works, and the sort of bubble that I didn't write down on the board, that works as long as the limits exist. So if
you
we
need
take
to
the
know if it
limit,
exists.
in the denominator, we end up with infinity. And if we take the limit in the numerator, we end up with infinity.
Well, since it's just one single term in the denominator, can't we just split it up so it would be ln over x and 1?
So we could rewrite this guy.
Take derivatives.
Okay, yeah, so I kind of like this observation about if we did split this up, and we looked at the top and we looked at the bottom, we'd end up with infinity over infinity.
L'Hopital's rule.
Yeah, and so here we have something that looks an awful lot like an expression that we can use L'Hopital's rule on. Now, what did L'Hopital's rule say? L'Hopital's rule said that if we have an indeterminate form, which we do, then we can take the derivative on the top, the derivative on the bottom, and then evaluate that limit and see what happens. Now, L'Hopital's rule says that we need to use derivatives. That makes 0 sense whatsoever because our graphs, the graph of this sequence is a bunch of dots. So how the heck can you possibly talk about a derivative when your graph is a bunch of dots? Totally weird. Okay? It turns out that what happens is that if you can kind of imagine that all the dots can be connected by a continuous function like this one, then you can use L'Hopital on the original function. And so there's actually a theorem that goes along with this. So this sequence requires L'Hopital's rule. But L'Hopital is a derivative rule. And this does not make sense for just having a bunch of points. Alright, so it turns out that all is not lost and we can still be in love with L'Hopital. And it turns out that there's a theorem that says if the limit as x approaches infinity of f of x equals L and f of n is equal to an for every integer n, then the limit as n goes to infinity of an is also equal to that same limit. Alright, so why is this useful? Well, this is really useful because it says that if we have a bunch of dots that we're looking at what happens to those dots as n gets really big, if we can replace those dots with some kind of a curve, like a function with x, which is a real number, and we can plug in that entire curve, and the dots exactly match up with the curve, then we can evaluate this limit over here, which means we can use L'Hopital's rule on this guy. Okay? So here's what we need to do. Over n. And what we're going to do is we're going to replace these n's, which remember n goes 1, 2, 3, 4, 5. There's no decimal values in there for n, no pi, no e, no anything except for whole numbers 1, 2, 3, 4. And we're going to replace that with the function natural log of x over x. Now x is allowed to be any real number, and so we get an entire curve, and we're going to take the limit as x approaches infinity. And the reason I can do that, the reason I can replace the dots with an entire curve is because of this theorem over here. It says that if you have a function f and you plug in the dots, then as long as that's equal to your sequence, then in other words, as long as the dots fit right along your curve, then you can replace the limit of your sequence with the limit of the function. Okay, so once we have this guy right here, now that we have something where we can use L'Hopital, this is of the form infinity over infinity. And so I can use L'Hopital. And so L'Hopital says that we have the limit as x goes to infinity. The derivative on the top is 1 over x. And the derivative on the bottom is 1. And so when we talked about L'Hopital before, after we took the derivative on the top and the bottom, the next thing we wanted to do is to simplify. And so here we have the limit as x approaches infinity of 1 over x. And as x gets stinking huge, what happens to 1 divided by that really huge number? It goes to 0. And so our limit is equal to 0. And so we can conclude that an equal to the natural log of n over n converges to 0. Alright, so L'Hopital is a really good tool to have. The only thing that we have to do if we want to use L'Hopital is to say, okay, here's our funky collection of dots. We're going to replace that with a curve where the curve exactly fits the dots that we have. And once we have our curve, then we can talk about derivatives and we can use L'Hopital if necessary.
Do we ever get dots that can't be mashed up to a function? Because wouldn't they always, I mean, if you have n, you just replace x as a function?
No. These sequences can get pretty weird. So, and for example, like, I just dropped my word. Factorials, for example, can show up in these sequences, but you don't really see them, you can't really talk about a derivative of a factorial. Things like that. So yeah. It's a big help, but it doesn't help all the time. Okay, so let's take a look at our next example. An is equal to cosine of n times pi over n. All right, now this cosine of n times pi, that showed up at the very beginning of class, right? What happened when you saw that cosine of n times pi? What was happening there? Yeah, we're having some sort of alternating going on. And so if I were to write out a few terms of this sequence just for kicks here, well, my first term, maybe I'll write them out as A1. A1 is cosine of 1 times pi over 1. And so cosine of pi is -1, so we have -1 over 1. A2 will be cosine of 2 pi over 2. And so that is +1 over 2. A3 will be cosine of 3 pi over 3. So that would be -1 over 3. And so what I can see here is that my sequence is going to look like -1, +1/2, -1/3, +1/4, -1/5, etc. All right, now thinking about the tools that we have, our goal is to figure out whether this sequence converges or diverges.
Isn't the wave itself getting smaller and smaller, closing down to 0?
Yeah, so our morally and ethically, we're thinking that this this sequence is probably going to converge to 0. Because as we look at these numbers, if we draw a picture of this sequence, we've got when n is equal to 1, our height is -1. When n is equal to 2, our height is +1/2. 3 is negative 1/3. When n equals 4, our height is positive 1/4, negative 1/5. And so these dots are alternating back and forth above and below the line y equals 0. But as they do that, they look like they're kind of getting sucked into the muck of y equals 0. So if I were to draw a tube around y equals 0, I can imagine that these dots are eventually going to always be within that tube. And so we think and we believe with all of our heart that this sequence converges to 0. Now, talking about muck and dots falling into the muck is not so mathematically sound. And so what we want to be able to do is to convey to others that the answer that we believe is correct is in fact correct. And so we want to be able to justify our answer. Now, the tools that we have, the first tool, this idea of looking at highest power on the top and the bottom doesn't apply because we have a trig function here. And if I think about our next idea, ooh, I love L'Hopital. Let's see if we can talk about L'Hopital's rule. And so I might think to myself, cosine of x times pi divided by x, well, our denominator would go to infinity, but our numerator is going to be bouncing back and forth between plus and minus 1, is not approaching any specific value. And so L'Hopital is out. Okay, because our numerator and our denominator did not give us one of those indeterminate forms. Alright, so this kind of leaves us with a problem. We have these dots that are bouncing up and down, above and below y equals 0, but they're not all on one side. If I just had 1 over n, I'd know about the limit for that, but I've got this alternating thing up there. And so the tool that I want to tell you about now is something called the squeeze theorem. And so it looks like our sequence is approaching 0. But it's bouncing all around as it goes to 0. So I'm going to write down the formula for my sequence, cosine of n times pi over n. And what I'm going to do is I'm going to squeeze this term between two functions that both approach 0. So what I might think about here is cosine of n times pi. What's the biggest that can be? Yeah, positive 1. And so if I replace that numerator with a positive 1, that's the biggest that numerator can be, and leave my n on the bottom, then I've got a squeeze from the top. On the other hand, what is the smallest that my numerator can be? Negative 1. And so I can bound my sequence below by negative 1 over n. So my sequence is always between negative 1 over n and positive 1 over n. Notice my denominators are all exactly the same, so I'm really just focused on that numerator up there. All right, now as n gets really big, what happens to 1 over n? Yeah, this goes to 0. So as n goes to infinity, 1 over n goes to 0. And as n goes to infinity, what happens to negative 1 divided by n? Yeah, that also goes to 0. And so the thing that's above my sequence and the thing that's below my sequence are both approaching 0. That forces this middle guy to automatically have to go to 0. All right, so our sequence was forced by squeezing to be squeezed to 0. And so in the end, we can conclude that the sequence an equal to cosine of n times pi over n converges to 0 by the squeeze theorem. says, and this is a rough statement of the squeeze theorem. If you want the correct squeeze theorem with all of its details, then you should look at page 414. But basically what the squeeze theorem says is that squeezing a sequence between two sequences that converge to the same value so squeezing a sequence between two sequences that converge to the same value tells us the squeezed sequence also converges to that value. Some textbooks don't call this the squeeze theorem, they call it the sandwich theorem. So these are your two pieces of bread, and they're forcing the lunch meat in the middle to go to the same value that the bread went to.
Now, if your sides like don't match, does that mean it diverges then?
No, if your sides don't match, that means that you have failed to squeeze the guy in the middle.
So in order to squeeze, they have to be equal.
That's right, that's right. Yes. It's possible that you might have just made bad choices on the left and the right side, and maybe this guy still does converge, or maybe the sequence doesn't converge and
You just can't find.
you just can't do it. Yeah.
And it is very specifically for converging sides, right? It wouldn't work if they were both going to equality.
That's exactly right. So the squeeze theorem is strictly a tool to show that a sequence converges. So if your sequence is a diverging sequence, then your squeeze theorem does nothing for you. You throw it off to the side, it's no good. All right, other questions about the squeeze theorem? I want to do one more example of the squeeze theorem. Okay. All right, so this sequence should look familiar to you. This is the sequence an equals 2 plus negative 1 to the n over n. So this was the second sequence that we looked at when we first introduced sequences. And so the question is, does this series converge or diverge? Does this sequence converge or diverge? Now, when we looked at this before, we drew a picture, and we ended up saying that, well, we kind of have this line around y is equal to 2, and our first term, a1 is equal to 1, a2 was half above 2, a3 was a third below, then a4 was a quarter above, a5 was a fifth below. And so it looks like what we have here is a bunch of dots that are bouncing back and forth above and below this line y equals 2. And we kind of think that this sequence, we believe, we morally and ethically believe with all our heart and soul, we believe that an, our sequence, converges to 2. But morals and ethics do not really apply when we're trying to prove that something is true or false in mathematics. And so we can believe with all our heart, but now we have to convince everybody else. Okay? So to convince everybody else, we have a couple of ideas. We do eventually want to calculate the limit as n approaches, actually I'll put this over here. We want to calculate the limit as n approaches infinity. Of 2 plus plus -1 to the n over n. And so I look at this, and I don't have my tools about rational function. I have this alternating piece, this -1 raised to a power. As soon as I have one of those, then I can't really use that highest power technique. And I can't use L'Hopital because L'Hopital would have -1 raised to an x, and I don't really know how to find a derivative of that. And besides that, this term doesn't go off to infinity on the top. So L'Hopital is out as well. So when I look at this sequence and I see that it's bouncing back and forth across this 2, and I morally and ethically believe that this sequence converges, I might try using the squeeze theorem. The squeeze theorem helps out a lot when your sequence is bouncing up and down, but yet you still believe that the sequence converges. Okay, so the very first thing that we might do here is we can use our basic tools for limits that says that we can split this up into 2 separate limits. So we can look at this as the limit as n approaches infinity of 2 plus the limit as n approaches infinity of -1 to the n over n. So this first limit here, this one's super easy because there are no n's involved in this 2. So as n goes to infinity, the 2 just stays as a 2. And so our limit is equal to 2. So we have 2 plus the limit as n approaches infinity of -1 to the n over n. Now this alternating part, this is the part where the squeeze theorem is really useful. So I'm going to look at -1 raised to the n over n, and I'm going to try and bound that above and below by some other sequences. So the squeeze theorem is really useful when you have an alternating part, a part that bounces up and down, because you know what the highest value is going to be. -1 raised to the n, what's the biggest that can possibly be?
1.
Yeah, the biggest that can be is 1. And so I've got 1 over n is greater than -1 to the n over n. The smallest that this numerator can be is going to be -1. And so what I've done is I've taken the term that I'm interested in, the -1 to the n over n, and I have put it between -1 over n and +1 over n. So now let's see what happens. As n goes to infinity, 1 over n goes to 0. And as n goes to infinity, -1 over n also goes to 0. So the 2 guys on either side of our mystery sequence, the mystery term that we're looking at, they both went to 0, and so our middle term was forced to squeeze to 0. And so this is our squeeze theorem at work right here. And by having that justification, I now know that this limit, as n goes to infinity of -1 to the n over n, is equal to 0. By the squeeze theorem. And so now we have 2 plus 0, which gives us 2. And so we can conclude that the sequence an equal to 2 plus -1 to the n over n converges to 2. So now we have a much stronger argument here. Rather than just looking over here and saying, look at these dots, they kind of look like they're getting close to this y equals 2, and that looks really pretty, and in my heart I believe that these dots are going to stay here really close to this line y equals 2, and that's really nice. But mathematically, we're much more rigorous now because we have split up our sequence. The limit of a constant is that constant. And for our second term here, which bounced up and down, we squeezed that term between 2 known sequences and showed that that limit goes to 0.
Are you going to want us to show all that? Or isn't it kind of obvious that
-1 to n is just gonna bounce back and forth between plus and minus 1 over infinity, so I mean, it's gonna be 0 regardless, there's just that 2 in there. Right, so the idea here is that, yes, I do want you to show the what it is specifically that you're squeezing. So it does become obvious. I mean, once you've done like 2 or 3 of these, and you say, oh yeah, that top number is not going any higher than 1 or any lower than -1, so this term must go to 0. In your head, what you're really doing is essentially a squeeze here. So yes, I do want you to show that. Okay, other questions? Okay. All right. So that wraps up our section on sequences. Now for the next few weeks, at least 2, maybe more weeks, we are going to be talking about sections 8.2 through 8 point whatever the last section is in chapter 8. And that topic is the topic of series. And today, for our last 10 minutes of class, I want to introduce you to what is a series. You're all now experts on sequences, so now we're going to build on that. 8.2 is an introduction to series. Alright, we're going to talk about a bouncing ball. A ball is thrown in the air to a height of 6 feet. Every time the ball bounces, it reaches 5/6 of its previous height. Alright, so this is a theoretical ball, so we're not worried too much about gravity here. This is just total theoretical model here. So the ball starts and it's tossed into the air. So at time 0, if I have time along the x-axis and I have height over here, then the ball is tossed in the air and it reaches a height of 1, 2, 3, 4, 5, 6. My height is in feet. So the first time the ball is tossed in the air, it reaches a height of 6 feet and then drops back down. And then the next time that the ball is tossed, and then the ball hits the ground, and then it goes up to a height of 5/6 of that, which is up to 5 feet, and bounces back down. And then the next time it's going to go to 5/6 of that. And so I might start to create a table. So in our first cycle, a cycle is a toss, so start from the ground, tossed up to 6 feet, and comes back down, so this is one cycle. So in the first cycle, the maximum height is 6 feet. In the second cycle, the max is 5 feet because we're going to take the previous cycle and multiply it by 5/6. So we end up with 5 feet. Okay. All right. After that, our next cycle is going to be 5/6 of the 5 feet. Anybody have your calculator out? Please calculate 5 times 5/6.
4.17.
How much?
4.17.
Okay, so approximately 4.17. And the way that we get that number is that we took 5 times 5/6. Okay. Alright, so that goes roughly to here. And then the next one will go to 5/6 of that height. So in our fourth cycle, we'll be taking 5 times 5/6 times 5/6 again, and what do we get approximately? What is that? So here, whatever 4.17, we need 5/6 of that number.
So it's 4.17 times 5/6, right?
4.17 times 5/6.
3.47.
3.47, do I have a second on that number?
Yep.
Okay, great. So 3.47, now how did we get that? Well, we took 5 times 5/6, our previous number, times 5/6. Alright, so take a look at this. In our first bounce, our first cycle, we had a max height of 6 feet. In our second cycle, we did 6 times 5/6. In our next cycle, we took that previous one, which is 5, and multiplied it by 5/6 again. So, by the way, this 5 times 5/6 is really 6 times 5/6 times 5/6. So really, this guy is 6 times 5/6 squared. And our next one, the way that we got that was we took the previous number and multiplied it by 5/6 again. And so this one would be 6 times 5/6 squared, that guy up above, times another 5/6. So I could write that as 6 times 5/6 to the third. So if I wanted to continue doing this, then I could say for the nth cycle, well, for the nth cycle, I'm going to have 6 times 5/6 raised to some power. So let's take a look at those powers that I have here. In cycle 4, I raised to the third power. In cycle 3, I raised to the second power. In cycle 2, well, I guess I raised that to the first power. And for cycle 1, where's the 5/6 in the first cycle?
5/6 to 0 power.
Yeah, so this is really 6 times 5/6 to the 0 power. So I can really make this into a nice pattern of 6 times 5/6 raised to 1 less than the number over here on the left. Alright, so with this in mind, what we have here now is actually a sequence. We have a sequence AN where AN is equal to 6 times 5/6 raised to the n minus 1. And this sequence describes the max height of the ball at the nth bounce. Now, as time moves on, as the number of bounces continues off to infinity, as the limit as n goes to infinity of 6 times 5/6 to the n minus 1, if I take that limit, well, I can bring that 6 out in front, and I have 6 times the limit as n goes to infinity of 5/6 raised to the n minus 1. And if I look at this limit, something I can think about here, 5/6, is that number greater than or less than 1? Yeah, this number is less than 1, smaller than 1. Now, if you take a fractional value, a number between 0 and 1, and you raise it to a really large power, what happens to that? Yeah, it gets really, really tiny. And so as n gets big, this entire term is going to 0. So we end up with 6 times 0, which is 0. And that's what we expect. We expect that as time marches forward, the height of the ball is approaching 0. It never officially stops because at any particular cycle time, any particular n value, you still have a height, but that height may be so small that we can't even see it anymore, but there is still a height. So the height of the ball approaches 0. Okay, now I promised you I would talk about something other than sequences. And so we have a maximum height here, and we can make a sequence, a list of numbers, that describes the maximum height. A second question that we might ask is, okay, how far has the ball traveled? And so we might create a second column here, well actually I guess it's a third column, which is total vertical distance traveled. All right, so think about this ball. This ball is bouncing, it's going straight up and coming straight back down. We do have these humps here, but that's because time is marching forward. The ball itself is bouncing, going straight up and coming straight down. So at the end of the first cycle, the ball has traveled 6 feet up, 6 feet down, for a total of 12 feet. All right. After the second cycle, the ball has traveled, so 6 feet up, 6 feet down, and then 5 feet up and 5 feet down. So in our second one, we've got 12 plus 10. All right. Now our next one down, so now the total distance after the third cycle, we've gone 6 feet up and 6 feet down, that's 12. And then we've gone 5 feet up and 5 feet down from our second cycle. And now we're adding on, well, here's our height for our third cycle. And we have to go up that height and then back down. And so we have to do twice this number right here. So plus 2 times 6 times 5, 6 squared. So take a look at what's happening with these numbers. If we want to figure out how far the ball has traveled, if we allow time to go on forever and the number of cycles to go on forever, what we're doing is at each time right here, at each step, we are adding all the previous distances and then adding on one more distance. And so the idea is, if we want to know how far the ball has traveled forever, meaning from our starting point to forever in time, then what we have to do is we need to add up an infinite number of numbers. And so our total distance traveled is equal to 12 plus 10 plus, 2 times 6 is 12, times 5, 6 squared. And then we keep on adding on more and more pieces. And so we end up with an infinite sum, and this infinite sum of numbers is called a series. So we now have a new idea here. Instead of listing numbers with commas in between them, We're going to start adding up a bunch of numbers. So we're going to eventually figure out exactly how far this ball is traveling. All right, so that's what a series is. We're going to learn more about them on Monday. So thank you for listening.